Thank you very much. So let me start by thanking the organizers for the invitation. So what I'm going to talk about is this article here, the goal of which was to try and reformulate integrable field theories in terms of affine Gaudin models. So there are two reasons why you'd want to do this. The first one is that all the field theories in question are so-called non-ultralocal, so I'll explain what that means in due course. And the problem with non-ultralocal theories is there's no general way of quantizing them. So the hope is that by formulating them as affine Gaudin models, this provides a framework within which to quantize them. The second motivation is that, as I'll explain in this talk, there's a very close parallel between the description of the spectrum of finite Gaudin models and the so-called ODM correspondence, which is a very nice duality between quantum and classical integrable field theories. So what I want to start with is giving you a very quick overview of the ODM correspondence for KdV, which is based on some very nice papers by Bazhanov, Lukyanov, and Zamolodchikov. So the starting point is to consider the Virasoro algebra, which is spanned by the modes Ln for all integers n, and the relations of the algebra given by as follows, where T is this combination of the Virasoro modes, and delta is this Dirac distribution. And so this can be regarded as a quantization of KdV in the following sense. If you define h bar as 1 over c, roughly, the central charge, and you take h bar to 0, or in other words, c, the central charge to infinity, and you scale the operator t as follows, and the Poisson bracket as usual, or the commutator as usual to get the Poisson bracket, then the field U satisfies the second KdV Poisson bracket, so it's the KdV field. And what's nice about this Virasoro algebra is that if you take the enveloping algebra and take a completion of that, then there's a very large commutative subalgebra of this completion. So the reason you need the completion is to make sense, for example, of this integral of the normal ordered product of T, because this is, in terms of modes, this is an infinite sum of all modes of Ln times L minus n. And what's nice also is that this third Hamiltonian, so they're indexed by exponents of the affine Kac-Moody algebra SL2, the third one is, in a classical limit, becomes the Hamiltonian of classical KdV theory. So this is really regarded as a quantization of KdV. And so once you have a large commutative subalgebra, you can ask what's the eigenvalues of this algebra on a given Hilbert space. So consider the Verma module of the Virasoro algebra with highest weight delta. So this Verma module is parameterized by the central charge and this delta. It's induced from a one-dimensional representation of the positive part of the Virasoro algebra. So more precisely, what this Hilbert space looks like is just the highest weight is killed by all the positive modes of the Virasoro algebra. The L0 has eigenvalue delta on this highest weight, and then all the other states are obtained by inducing with negative modes. Okay. So if you think back at the Hamiltonians, so the first thing you're trying to diagonalize is L0. And so because all these things commute, it's good enough to think about how to diagonalize on the eigenspaces of L0. And these are just given by these subspaces at a given level below the vacuum. Okay, so the aim will be to diagonalize these Hamiltonians on any of these finite dimensional subspaces, VL. And so the first thing to note is that the dimension of these spaces is exactly the number of partitions of the integer L. Okay, so we have a direct sum decomposition of the Verma module into these graded subspaces, VL. So the remarkable observation of Bazhanov, Lukyanov, and Zamolodchikov, based on earlier observations by Doré and Tadeo, is that the joint spectrum of the KdV integrals of motion on this finite dimensional vector space VL is in one-to-one correspondence with certain Schrodinger operators. So second-order differential operators with some potential, which I'm not writing, but I'll write on the next slide. And these were operators which appeared in Lotte Holland's talk. She called these op-pairs because this is really an op-pair for, or in fact, if you add this E, this is an op-pair for the SL2 Kac-Moody algebra. These op-pairs have singularities at 0 and infinity, so they're defined on the punctured plane, with extra punctures 1 to L, W1 to L, depending on which subspace you're diagonalizing them on. So if you're diagonalizing on the eigenspace of level L, you have L extra punctures, and these punctures are localized at very special positions, which are determined by L algebraic equations, which are independent of the energy E. And the nice fact is that, first of all, in counting-wise, this makes sense because the number of solutions of these algebraic equations matches the number of partitions of the integer L. Okay. So I'm not going to explain exactly how you extract the eigenvalues from these operators, but as Lotte mentioned in her talk, the eigenvalues of certain quantum integrable systems can be described precisely by op pairs. So you can regard the op pair as an eigenvalue, as a joint eigenvalue of these commuting Hamiltonians. So what I want to focus on in this talk is the reformulation of this correspondence by Fagan and Frenkel in 2007, where they really identified the Schrodinger operators with affine op pairs for the Lie algebra SL2. And they interpreted these algebraic equations as monogamy-free conditions on these extra singularities at Wi. So what an op pair is really just a rational SL2 valued connection, valued in the Kac-Moody algebra SL2, which are Borel valued almost, but they have this lower one and the lambda inverse, which are not in the Borel subalgebra. So this is just a negative nilpotent simple root generators. And otherwise, it's all Borel valued. And so you look at these operators modulo this gauge transformation valued in the unipotent subgroup of the Kac-Moody group. Okay, so and then there's a precise matching between the parameters entering here and the original parameters of the module C and delta. Okay, so this is all very explicit. And what I want to stress is that what allowed Fagan-Frenkel to reformulate this and in fact extend it to a description of the spectrum of GKDV for any Lie algebra G is the observation that KDV theory, GKDV theory, is actually an affine Gaudin model. And this is, so what I want to describe next is how in the finite setting, if the Lie algebra G is finite, a G Gaudin model has a description, its spectrum is described precisely by op pairs, but not for affine Kac-Moody algebras, but rather for finite Lie algebras. So let me briefly describe this. So the data for defining a Gaudin model is just a semi-simple Lie algebra G over C. Yeah, sure. Yeah. Yeah, so yeah, this Schrodinger operator is equivalent to this op pair I wrote on the board. So in fact, from here you could read off this capital V potential. And the lambda inverse is precisely the energy. So this is the energy term in the previous formulation. And the potential is essentially what's here in this expression. Yeah, this I'll describe towards the end, yeah. But so you're saying you do the spectral analysis of this Schrodinger operator, you take Wronskians of solutions, and these are satisfy TQ relations. Yeah, this I'll describe at the end. But yeah, so this is how you sort of match both sides without knowing that there's an underlying Gaudin model. But the point is, if you know there's an underlying Gaudin model, then I claim that there's a more direct relation between these two. Because if you think of your KDV theory as a Gaudin model, then at least conjecturally, the Gaudin model, its spectrum is described by op pairs. So this is a more direct link. Okay. So in the finite dimensional setting, this is how it works. You pick some dual bases of the finite Lie algebra with respect to some non-degenerate invariant bilinear form. And then you pick some finite set of points, n points on the complex plane. And then the quadratic Gaudin Hamiltonians are given by this expression. They live in the n-fold tensor product of the universal enveloping algebra. And I use this standard notation that x to the I means that you take this Lie algebra element in the ith tensor factor. Okay. So there are two nice properties of these Hamiltonians. First of all, they commute with the diagonal action of the Lie algebra. This will be important later. And then secondly, they commute amongst themselves. So you have a commutative family of Hamiltonians. There are n of them for the moment. And you can ask whether, because they commute, do they belong to a larger commutative algebra within the enveloping algebra? And it turns out that they do. In fact, for rank greater than 2, there's more than the Gaudin Hamiltonians. There are higher Gaudin Hamiltonians. And so they belong to this larger algebra called the Gaudin algebra, which is a commutative subalgebra of the n-fold tensor product of U of G. And they also happen to commute with the diagonal action of G. This is what signifies this superscript G. They commute with the diagonal action of G. So given this large commutative subalgebra, you can ask, given a spin chain now, what is the joint spectrum of this Gaudin algebra on the spin chain? So I want to consider here finite dimensional representation. So I take n integral dominant weights, lambda 1 to lambda n, and the corresponding irreducibles. And the question is, what is the joint spectrum on this tensor product of finite dimensional modules? And so because the Gaudin algebra commutes with a diagonal action, it's enough to restrict attention to the subspace of singular vectors inside this tensor product. In fact, you can think of all the singular vectors of any given positive weight, integral dominant weight. So lambda infinity will be the weight of the singular vector inside this tensor product. And so the joint spectrum on this subspace is given precisely, or it was conjectured by Frenkel in 2004 and proved recently by Rybnikov, that the spectrum is given by OPERS for the Langlands dual Lie algebra. So underlying this is, in fact, the Langlands correspondence. If you can relate this to the talks of Donaghy and so on. So there's some very deep theory behind this. But these are just OPERS, roughly. I'll describe an example later. Which have regular singularities at the zi's and at infinity with residues fixed by these weights. Specifically, they're given by shifted Weyl orbits of these weights. And moreover, these OPERS have no monogamy as well. Okay, so most of the OPERS in this family actually come from the following. So this is related to the beta ansatz for Godown models, and I'll give the example in SL2. You consider operators of this form. So these are called Mura OPERS. They're Cartan connections with an extra 1 below the diagonal. And the U here has just regular singularities at the zi's with residue the lambda i's. And then extra singularities at the wi's. So there are m of these. And the residues are just simple roots of the finite Lie algebra. And so the condition that this OPER has no monogamy at these points, so in fact no singularity at these points, is given by m algebraic equations on these points, which are the beta equations. Okay, and note that lambda infinity here is just the residue at infinity of this Cartan connection. So it's given by the lambda i's minus the sum of all the simple roots. Okay, and so what you consider is this Mura OPER modulo gauge transformations valued in the Borel's in the unipotent subgroup, and these are exactly OPERs of this form. Okay. Any questions so far? Yeah. Ken, sorry? Lambda binipotent? Which? The residues are Cartan valued, so they're weights. So they're living in the dual Cartan subalgebra. So they're positive integral dominant weights. Okay. So now let me move on to the main subject of the talks, which is how to reformulate field theories in terms of affine Gaudin models. So the setup is really the same as before, except you just replace the finite Lie algebra by Kac-Moody algebra. So I take the untwisted Kac-Moody algebra, G twiddle. So it's the loop algebra plus the central extension plus the derivation. There's a canonical basis for this loop algebra, and it's dual with respect to the bilinear form and the Kac-Moody algebra. And then, to be a bit more general than what I was before, rather than just pick a set of points, I pick a set of points and some positive integers attached to each of these points. So this is what's called an effective divisor. So this will define more general Gaudin models, so that's why it's called generalized affine Gaudin models. And so the example I'll follow, because it's very technical if I keep it general, I'll stick to the example with two simple poles at the origin, so a double pole at the origin and a double pole at infinity. So to this divisor and this data, we associate what's called Takif algebras, which are just truncated polynomial algebras. So you take the polynomial algebra over G twiddle, and then you truncate it at order 2. So really it's just a Kac-Moody algebra plus an abelian copy of the Kac-Moody algebra. Epsilon naught is a nilpotent, it squares to 0. Okay, so this Takif algebra has a canonical basis, which is given by generators of the Kac-Moody algebra tensor 1 or tensor epsilon naught. And you do the same thing at infinity. The subtlety is just infinity is rather special in this context, and you start off at the Takif algebra at level 1. So there's no level 0 at infinity for technical reasons. And so the Takif algebra at infinity, because it's also of degree 2, it just contains this abelian Lie algebra, epsilon infinity times Kac-Moody algebra. And so the generators are given as follows. So the notation is the superscript is the point to which the generators are attached, and the subscript is the degree of the Takif algebra. Okay. So given these Takif algebras assigned to each of the points of the divisor, you take their formal direct sum, and this will be the algebra called G twiddle D. So it's associated to Kac-Moody algebra and a choice of divisor. And I emphasize you can do this for any choice of divisor. So what are the fields of the Gaudin model? And these will turn out to be the fields of the integrable field theory. So you just take these canonical elements which pair the Kac-Moody generators in the auxiliary space with the generators of the Takif algebra in the quantum space. So this is an element of the completion of the tensor product of Kac-Moody with the direct sum of Takif algebras. And so you have two fields attached to 0, the one with index 0 and 1. and then you have one field attached to infinity with the index 1. So just 3 fields. And you can very easily show, so using this tensor product notation, where if you take this field, which is valued in a tensor product of 2 algebras, you can consider the field subscript 1, which means you take the auxiliary space in the first tensor factor. Subscript 2 means you take the auxiliary space in the second tensor factor. And then you have this, for example, split Casimir, which lives in the first and second tensor factors, which is a canonical, it's the split tensor Casimir for G twiddle. And so in this notation, we have the following Poisson brackets, where this Poisson bracket is just commutator on the quantum space. It's just a notation for commutator. In fact, if you were to think of this as a quantum affine Gaudin model, then the commutator would just be written as a commutator, and it's exactly the same relations. So these are the Poisson bracket relations for these formal fields, and what I want to emphasize here is just that the field at infinity is really a Casimir of the algebra. This will be important. So what do we do with these formal fields? Well, if we write out the formal field at each point in the explicit basis, we have these 2 terms corresponding to the central extension and the derivation, and then we have the loopy bit. And the loopy bit will turn out to be the field. So what we do is we apply a representation to the auxiliary space. We represent the Kac-Moody algebra in terms of G-valued connections. So we represent D by the derivative on the circle. K is sent to 0, and then these loopy modes are sent to Fourier modes on the circle, G-valued Fourier modes. And then the other representation you apply to the quantum space is more technical, but all that matters here is that the operators corresponding to the central charge are sent to levels, to some numbers, okay? Yep. Yeah, so just because of this, so this will turn out to be a field. So I call these things formal fields. They're not quite fields. They turn out to be connections. But these are really the classical fields of the model. So if you pull out this factor of IA here, then what you're left with is this formal infinite sum, which you can regard as defining an operator-valued formal distribution on the circle, in the sense that if you pair it, if you integrate it against a trigonometric polynomial on the circle, what you get is a finite sum of these operators. So it defines an operator-valued distribution, formal distribution on the circle, which is really just a classical field, which is a precursor to a quantum field. Okay, so to define the model, you further specify what the levels are. So the reason I've been considering this this divisor, 2 copies of 0 and 2 copies of infinity, is because this will turn out to be related to the principal Carr model. And so to define the principal Carr model, I choose these 3 levels. And so doing so, for example, L0 means that there's no derivative terms in the formal field at 0. There's a derivative term with coefficient 1 in the formal field Takif level 1 at 0. And the name for this field in purple is J0 for the one at the origin level 0, and the level 1 is called J1. And then at infinity, recall that the mode at infinity was a Casimir, so I can freely set it to 0. And so there's no field at infinity, just a derivative operator. And so now if you apply a tensor product of representations to this algebra, this Poisson algebra, you recover the Poisson algebra of the principal Carr model. So if you're familiar with this, then you recognize this algebra. Otherwise, this is just the Poisson bracket for the principal Carr model current J0, its components J0 and J1, which are defined by G inverse dG, which G is being the principal Carr model field. And this delta prime term is the famous non-ultralocal term in this Poisson bracket algebra, which makes it hard to quantize. Okay. So you can also define the formal lax matrix of the Godown model, which is a formal linear combination of the fields, of the formal fields, and it satisfies this standard RLL Poisson bracket. Okay, thanks. And if you apply to this lax matrix this tensor product of representations, then what you recover is the lax matrix of the principal Carr model, and also the coefficient of the derivative term. So this is a connection, it's a lax connection. And what you get as the coefficient of the derivative is what's called the twist function. So this appears in the Poisson structure of the lax matrix. So this is a famous non-ultralocal Poisson structure identified by Semnov, Chanchansky, and also Maillet. So there's this delta prime term again. And the R matrix is twisted here by the twist function. So the lax matrix here by above just satisfies this Poisson algebra. Okay. So let me come to the conclusion. So what I wanted to emphasize is that dihedral Gaudin models can give an formal algebraic formulation of non-ultralocal integrable field theories, and the hope is that you can quantize these theories within this framework of Gaudin models. So how does quantization work in the finite setting? Well, the finite Gaudin model is defined as exactly as I specified earlier, but instead of working in the universal enveloping algebra, you just work in the symmetric algebra over G. So it's a Poisson algebra, and you take its n-fold tensor product. This is the algebra of observables of the classical Gaudin model. And to quantize it, you just replace it by the universal enveloping algebra, its n-fold tensor product. And so the question in the field theory case is to identify the relevant completion of this algebra, enveloping algebra of the Kac-Moody algebra. So it's similar to the completion I described in the first slide. For the Virasoro algebra, you take a completion of the enveloping algebra, and this is the adequate algebra of observables within which the KdV Hamiltonians live. So let me come back also to the ODIM correspondence and make a comment on this. So as you mentioned earlier, so typically the way that the ODIM correspondence works is that you have a quantum integrable field theory, and the conjecture is that its spectrum is described by op-pairs. And the way you connect the two sides of the correspondence is, on the one hand, you can compute spectral determinants of this differential operator, and you find functional relations by WKB analysis which are exactly of the form of a TQ system, Baxter TQ system. And you can match this with the TQ system obtained on the other side. So in the KdV theory, the nice thing about KdV theory is that it's ultra-localizable. So there's both a non-ultralocal formulation and an ultralocal formulation. The ultralocal formulation is the one within which you can use the RTT formulation, which was described, for example, in the talk by Costello. So the RTT formulation is exactly what you have when you have an ultralocal formulation of a model. And from this RTT formulation, you can extract also functional TQ relations of Baxter type. And the point is that on both sides, they match. You get the same relations. What I want to stress is that if a theory is not necessarily ultra-localizable, you might not have access to this RTT formulation. But because a non-ultralocal theory is always as I showed, it's a classical Gaudin model, you can hope to quantize it as such and make a direct connection with op-pairs, provided you can generalize this theorem of Fagan-Frenkel connecting finite Gaudin models to finite op-pairs, generalizing it to the affine case. Okay, so one thing I didn't mention at all is what the word dihedral means, so let me just quickly finish with this. So you can generalize Gaudin models in many different ways, and one way is to define what's called cyclotomic Gaudin models. So what these are just Gaudin models invariant under some cyclic symmetry. So the lax matrix of the model is ZT equivariant, where ZT is the cyclic group of order T. So for example, if I take T equals 3, and I think of a Gaudin model with one site at X, if it's cyclotomic of order 3, then actually there's a corresponding sites at omega x and omega squared x, where omega is the third root of unity. And so if I attach a field to x, I need to attach the image of the field under some automorphism of order 3 to the image point and so on. So I have 3 sites, and the lax matrix has this form, and so it's equivariant in the sense that if you act with sigma on the lax matrix, it's the same thing as rotating z by omega. Okay. And you can actually also define op-pairs to describe the spectrum of these models. So these are cyclotomic op-pairs. And most of the technology goes through, so it's conjectural for the moment, but many of the results about Gaudin models go through in the cyclotomic case. So what is dihedrality? Well, it's just imposing further reality conditions. So reality conditions, in other words, invariance under the reflection in the complex plane promotes the cyclic group to a dihedral group. So you have an action of the dihedral group on the complex plane, and correspondingly, you should use an antilinear automorphism on the Lie algebra, and you have an action of the dihedral group on the Lie algebra itself. And so your lax connections should be equivariant under this dihedral group. So what I want to finish with is this proposal that, in fact, the extension of the Gaudin op-pair correspondence for finite Gaudin models to the dihedral case should look as follows. So in the complex case, you have basically op-pairs corresponding to the spectrum of the Gaudin model, but in the real case, you're basically going to have op-pairs, but also anti-holomorphic op-pairs, and together these form a total lax connection. So in fact, the spectrum of these dihedral Gaudin models should be described by solutions of the classical Toda for the Langlands dual Lie algebra, Toda field theory. And conjecturally, if you extend this to the affine setting by replacing the Lie algebra by its affine version, so G by G twiddle and the Langlands dual by its affine Kac-Moody algebra Langlands dual, then this looks very reminiscent of the massive ODM correspondence, which described the spectrum of massive integrable field theories in terms of affine total field theories. Okay, so that's it. Thank you.